Okay, so I want to start with a few administrative announcements. So the first thing is that the Learn webpage is on now. So you could check the Learn, and there should be the webpage. And one more thing, I put there, since the book is not in the bookstore yet, they promised me it will be there towards the end of next week. Then I put the chapter that covers the technical stuff that I did last time. The book chapter there is online on the Learn webpage. So for the technical stuff of last week, it is available online. Later, I'll just assume that you have access to the book. Yes?
Where are the videos?
Where are the videos? I don't know. I haven't got them yet. I mean, I have to nag them. I'll put them as soon as they... I want to have another web page. Probably I'll put them... I don't know. Is Piazza open to everybody or just to students which are registered to the course? Registered to the course. We also have a Piazza page. Please enroll to the Piazza, and then we can have discussions. You can ask questions. I hope that everybody is familiar with it. You enroll, and then it's kind of a news group, and we can have discussions and announcements there. And I will also have make a web page which will be open to students which are not registered, and that's where I'll put the videos. Yeah. Yeah. So I think these are my announcements. The main thing is that the chapter which contains the technical content is there, and the book will be in the bookstore towards the end of next week. I also owe an answer to a small question to you from last time about the rats. We don't have to give them poison that kills them. It's enough to give them poison that makes them feel bad. And then we just try to see if they associate the sick feeling with the food that they ate while they were hearing the bell. But we don't really have to kill them. Yeah. Okay. So what did we do last time? Let me summarize. I think that it was a bit technical, but I hope that I'll explain it now and it will not look as scary as it could. So we wanted to prove the following. We were considering so this is just a summary of last lecture. So we were considering the algorithm. So we're given a class H of predictors, say from our domain to 0, 1. So H in H is a function from x to 0, 1. And now we define a simple learning paradigm that we call ERMH. And what does ERMH? In general, what does a learner do? A learner gets a labeled sample and should output a function, a prediction function. So ERMH, when it gets a labeled sample S, what it outputs is a function that belongs to arg min over all H in H of the loss with respect to the sample of our function H. Okay, so let me explain this notation again. So this is you can think of it as an algorithm, a learner. So it gets as an input, it gets a sample S. This sample S looks like some sequence x1 with label y1 up to xm with label ym. That's the input of our learner. What will the learner output? the learner here goes over all h's in the class H. That's why the subscript capital H here. And picks one that has minimum loss with respect to S. The loss with respect to S is just the number of mistakes that you make on this sample. For every H, I can check how it behaves on each of those X's and compare it to the corresponding Y and count how many errors. And I want to output one of those that minimize the number of errors. So that's the empirical risk minimization paradigm. Why do I call it paradigm and not algorithm? Because it doesn't even tell you which H to pick. There could be many H's that minimize this loss. It just tells you pick one of them. So it's not a well-specified algorithm, not to talk about that we didn't talk at all about how to implement it and how difficult it may be to implement it. But that's, so I call it a learning paradigm. And what did we want to prove? So we had our first theorem. And our first theorem was that if H is a finite class, then for every f in H and every probability distribution D over X. Now I want to give you some kind of a guarantee of the success of this paradigm ERMH to learn the function f. So we want to say, I will use a slightly different notation that last time people commented to me that this notation may be confusing, so let me rewrite it like this. So I look at the probability of S being sampled according to D to the M. So this is the probability. Last time I used dm, but maybe it's more user-friendly to look at it like this. I look at the probability over S's that are generated by taking m times picking a point according to D. The probability that what will happen, that the arrow, the true arrow of ERM H of S will be greater than epsilon. This probability is bounded by the size of H times 1 minus epsilon to the power m. And this holds for every epsilon greater than 0 and every m. So that's what we proved last time. So let's just make sure that we can all parse it and understand what is being said here. So the scenario that we're describing is that there is here is my algorithm, and it takes as input S. We assume that S is generated by picking m times independently at random according to the distribution D. So this is the distribution over the domain. It tells you how to pick an X. You pick X m times. What is missing in there's something missing here that shows your chance to get your first bonus point for the course. What is missing here? Right. F is missing, so the procedure is that, okay, you didn't catch me, so I don't owe you a point, but next time raise your hand before I ask, okay? We need an F here, right? We need an F here because for the loss, I have to compare it to some real correct labeling. So this is the probability L of D F of any function H is, again, I will use this notation, is the probability when X is generated according to D, the probability that H of X will not equal F of X. So F is the rule that I use for labeling. And what I want to minimize is the probability that my predictor H will miss the labeling that is designed by F. So F assigns labels. So here is the probability over x's of a mistake in the future. Mistake in the future with respect to the function f. So this was the theorem that we proved last time. Any questions about it? Now, this is a very key result, and let me, before I discuss a little bit the proof, let me just improve this, kind of clean up this expression. So I will use just believe me, or trust that. The kind of things that I can then give you as part of the assignment, that for every epsilon greater than 0 and m, I can bound, this is not a nice expression, 1 minus epsilon to the power m. So this is a number less than 1, right? So epsilon, let's say, less than 1. This is a number less than 1. And when I take powers of it, it gets smaller and smaller and smaller. And I want to have some estimate on how fast it gets smaller. This is bounded by e to the minus epsilon m. So what I'm claiming, this is saying e is the base of the natural log, like 2.7. So what I'm saying here is that as m grows, this number goes to 0 exponentially fast. So we get here that the probability of making an error is going down exponentially fast in the sample size. For every m, it goes down exponentially fast in the sample size. So you set your precision parameter, and I'm using my ERM algorithm. I have quite a strong guarantee. If I have enough samples, I have quite a strong guarantee that my error will not exceed epsilon. Yes? What? The size of h. Oh, now you caught me. Right. OK, so you get the point. The size of h here, of course. Right. The size of h here. So the procedure is you send me an email, OK? Send me an email with your name. And you will do it? Don't promise to do it. OK? Yes?
What if I send you an email with my name first?
Yeah. I'll have to learn how to handle such issues, right? But I can warn you. I have on Learn, I have a table of the pictures of each of you from your student card. So when I get the email, it's a question of whether I still remember what did this guy look like. Yeah. OK, so there is an h here, the h that was here. Good. OK. Let me just say one thing about the proof. Again, I explained the proof last time. The proof consisted of two steps. The first step was saying, so the proof idea, the reason I want to repeat it because we will use it a lot. The proof idea consisted of two steps. So step one was showing that for any given h that goes from x to 0, 1, the probability over a sample that picks m points that for any such h, the probability of a sample that picks m point that the error LDF of H will be greater than epsilon is small, is small and getting smaller with M, provided that L S of H is 0. Okay, so let me, what we're doing here, we were looking at our space. This is my space of all S's. This is a space of all S's, all samples. And I'm looking at different samples. And I'm looking at all the samples. I pick some H, and these are all the samples provided that LS of H is bad, greater than epsilon. These are all the samples. Oh, now I'm getting now a lot of bonus points. The probability which is small is that this is 0, provided that it has error bigger than epsilon. Okay, the probability that I make the probability, lots of mistakes. I really apologize. Let me rephrase it. And this is LDF. Okay, let me rephrase it from here. I apologize. Let's read it again. What I'm saying is I fix some H. Assume that this is a bad H. A bad H is an H that its true error is greater than epsilon. Assume that this is a bad H. So I fixed an H which is a bad H. I want to say that the risk that ERM will pick it is small. When will ERM pick it? ERM pick it if on the sample it looks perfect. So I want to tell you that the risk that someone who is bad will really look perfect on the sample, this risk is very small. That's what the first step. So this is someone, LD of F of H is greater than epsilon, means this H is really bad with respect to distribution. This tells me, with respect to the sample, it has error 0. It tells me this guy looks, with respect to the sample, as if it's a great H. So this is a misleading H. Deceiving this H is deceives us. It's really bad, but it looks nice. We want to show that most of the sample will not lead us to such a confusion. And the reason is, so we are looking at all the samples that make H look good in spite of H being bad. Bad means it has error greater than epsilon. Look good means on the sample it looks like 0 error. And why is it small? It is small because if I look at all the area where H errs, and this is now just the space X, I look at all the points on which H errs, and here H behaves very nicely. It agrees with F. If H is a bad guy, what do I know about the area here where it errs? What do I know about the size of this area? The probability of a point falling here. Right, this is greater than epsilon. It's a bad H, therefore the area here of points on which it will give me the wrong answer is greater than epsilon. Now I'm picking points at random. When will it look perfect? It will look perfect if all the points fall outside the area where it makes mistakes. So the probability of one point falling outside this area is at least 1, is at most 1 times minus epsilon. the probability of the second point falling in this area is again at most 1 or minus epsilon. If I have m points in my sample, I get 1 minus epsilon to the m. So this probability of making mistake is bounded by this for my given h. Okay? For my given bad h, the probability of an S not detecting that it's bad is 1 minus epsilon for each sample point in S, and I have m such sample points. So I have m such sample points. Okay? Now, why doesn't this finish the proof? Here I showed you that given any h, if h is bad, ERM h will detect it. So why doesn't it finish the proof? What is missing here to make it a proof? Yes? What? This is only for a specific h. If I have many h's, then another h, maybe this sample will fool me. And for another h, maybe this sample will fool me. And if capital H is very big, I have to consider the samples that may fool me for each of them. So just to give you an idea of this, what we need here to demonstrate this idea, think of this very famous scam for how to make people give you money. So you tell them that you're sending an email to lots of people and telling them that you want to give them advice. They should buy your advice on how to invest in the stock market, say. And you send emails to 100,000 receivers, and to half of them you say the euro will go up next week, and to the other half you say the euro will go down next week. So those people get your emails. Usually they will not really pay a lot of attention to it, and for half of them you will be correct, for half of them you will not be correct, right? Then for those people that you were correct, you send them an email the following week and tell them, you remember that I was correct last week? I will show you now that I'm correct next week as well. So you divide them into two equal groups and send half of them an email saying next week the euro will go down. The other half you say next week the euro will go up. And now you are left after 2 weeks. There are 25,000 people that saw you being correct for 2 weeks consecutively. And now you keep doing this. And eventually you will have a small group of people that saw you being correct, I don't know, 10 weeks in succession or something. They are now tend to believe you, and they will be willing to invest their money to get your services. And you know nothing. You just gambled. Right? And this is exactly what is happening here. I mean, this is like 1 week. The probability that 1 week I'll be correct just by chance is, so what is happening here is the probability that I'm explaining this guy? So what I'm saying is that if I have many hypotheses, what I could think of this experiment as if I keep sending it to all my recipients. So actually what I'm sending them is the hypothesis that is will go up, will go down the first week. And then I'm sending half of them will go up, will go down, will go up, will go down. And then I'm sending to half of them up, down, up, down, up, down, up, down, and so on. And now for every sequence of 10 weeks, I have a hypothesis. It will be up, up, down, 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 up, down, up, down, up, down. For every sequence, I have such an hypothesis. If I have lots of hypotheses, I have a very good chance that at least one of them will be correct, even just by chance. And that is what's happening here. I have lots of hypotheses. This is like the hypothesis of what will happen in 10 weeks. What will happen after 10 samples? But if I have lots of hypotheses, there is a chance that just by coincidence, one of them will be correct. And we have to rule out all of this because we want to make sure that any ERM algorithm is not misleading us. So we need to also take into account how many samples we have, and this is step 2 of the algorithm of the proof. So step 2 of the proof, step 2, take union over all H in H. And that's where we got this H here. So the proof consists of 2 steps. One is to show that for a particular H, my chance of being correct is small, which is just saying for a particular prediction of how the stock market will behave for 10 weeks, my chance of being correct is very small. The next step is saying if the number of hypotheses that I have is finite, then I can take the union of all of them and have a bound on the probability that at least one of them will be correct just by chance. Yes?
If you have a large set of hypotheses and a small m, is the probability greater than 1?
Right. So it doesn't tell you anything, right? So we got here this, let me rewrite it. It's really ugly here. Let me rewrite it. We said the bound is the size of H times e to the minus epsilon m. So this probability will be meaningless if H is very big and m is small, for sure. But the bound will be correct. I mean, you say something meaningless, it's not a mistake. But what the important point to notice is that for every given H and every accuracy parameter, if m is big enough, then I'm guaranteed to succeed. OK? So that was just a recap of the technical part of last week. And this leads us to the formal definition of what do we mean by our first definition of a notion of learnability. OK, so our first notion of a formal notion of learnability. We will see other notions later, but we start with this one. We say that a class of predictors H is PAC learnable. And PAC stands for probably approximately correct. So we are not going to guarantee success. We are just going to tell you that you're going to be approximately correct. And even that, only probably will be approximately correct. So this is the PAC notion. We will see in a minute why do we need these kind of caveats. So a class is PAC learnable if there is a function. I'll call this function mh. The function depends on h. And this function mh goes from the interval, open interval 0, 1 times 0, 1. So it's the open square to the natural numbers, such that for every such that there exists a learner, and the learner for us is a function that takes samples and outputs hypotheses. So if I want to write a learner formally, it goes from the union over I goes from over M goes from 1 to infinity of X cross 0, 1 to the power M to the set of all functions, the set of all functions from X to 0, 1. OK, so here we have a little bit of notation. The reason I write it with this notation because I want you to get used to this type of notation. So let's just go over the notation, and then I'll continue with my definition. So what is a learner? A learner takes a sample as input. What is a sample? A sample is a sequence of pairs, a point from X and a label. And the sample has length m. So my learner should be able to take a sample of any length. So this is the union over all sample sizes. This is just denotes a sequence of points and labels of length m. This is the input that my learner takes. And what is the output of the learner? The output of a learner is a function. It's a predictor. A predictor is a function that goes from X, takes an input point in X, and predicts a label. So that's a learner. OK, so let's go back to our definition. So we say that a class is PAC learnable if I have a function such that there is a learner that for every D probability distribution over X and every F in H and every epsilon delta greater than 0, the probability over samples generated by D to the M and labeled by F that LDF of AS will be greater than epsilon is less than delta for every M which is above MH of epsilon delta. OK, it's a very scary definition, but we'll get used to it. We'll go over it now. We'll explain it again many times. So what does the definition tell us? What does this formula tell me? This formula tells me that I take samples the way we were taking samples before. They are generated according to D and labeled by F. I feed those samples to my algorithm, and I check what is the error that my algorithm makes. And I want to say it is unlikely that my algorithm will make an error greater than epsilon. The probability that it will make an error greater than epsilon is smaller than delta. So here I have my two parameters, the probability and the approximately. This is my algorithm is approximately correct. It may have an error of up to epsilon. And this is it probably will be the case, except for a delta fraction of the time of the samples. And learnability means that you give me how precise you want to be. And you give me how confident you want to be. So these two inputs here are the epsilon and the delta. So we can think of epsilon is our accuracy parameter. And delta is our confidence parameter. Oh, that's the probability. That's the delta. And the epsilon is the how approximate we are. OK, so we say a class is learnable if you tell me how accurate you want to be and what confidence. And after you tell me that, I can give you a number and guarantee that if you give me so many samples, you will really don't have to worry. With high probability, except from delta function of the samples, you will get a correctness with accuracy below epsilon, with error below epsilon. OK, any questions about this definition? This is going to be a key definition. Good that there are questions. Yes?
One in front of, like, one epsilon is greater than 0, and less than 1. This goes from the open unit square.
Yeah, but if epsilon is bigger, it makes life easier for me. Yeah. Yes?
Confirmation is also a function.
What?
A of s is also a separate function.
What is A of S?
A of s, yes.
Oh, A of S. You see, A is my learner. There exists a learner A, and A takes a sample as S. So what happens here is I pick a sample at random and feed this sample as input to A. So now A outputs some prediction rule. And I check the error of this prediction rule. So A is my learner, my learning algorithm. S is the input that it got, which was generated randomly. And A of S is a predictor. And now I want to bound the probability that this predictor will be bad. It will be bad with small probability if M was big enough. OK? Yes?
For the formula above, what does the double F mean?
Oh, yeah, it's not double F. Right. It's the set of all Fs. I don't know how. I mean, it's a really confusing notation. It's the set of all Fs such that F goes from X to 0, 1. Okay. The two semicolon here, they mean different things. This one means the set of all F such that, and this means F is a function from X to 0, 1. So I look here at the set of all functions from X to 0, 1. Yes?
So is MH a function which decides, based on your accuracy and confidence, how big your sample size is?
Right. MH is the function that, based on my accuracy and confidence, decides how big a sample. Assume that I want to have a survey. I'm a company that's making surveys, and you want to predict, say, the result of the elections. So I can ask you how accurately you wanted me to predict. You want me to give you a prediction within 1% or within 5% and so on. And I ask you how confident you want to be. Because no matter what prediction I give you, there is a small chance that it will be false. So you tell me I want prediction of 99%. So delta is going to be 1%. And you want to be accurate to within 2% of the results of the elections. So you give me these parameters, and I tell you, oh, in this case, I will have to sample MH of epsilon delta people. I will have to sample 1,500 people. So it will cost you such and such. So you tell me what are your accuracy and confidence parameters, and I can tell you what sample size will suffice. That doesn't what it means learnable. That and note that I don't have to know anything about the distribution that generates the data. Any more questions about the, yes?
So for the function A, the output has to be H, because each function is H, right?
The output, that's a good point. I mean, I don't require that the output will be from H. I mean, I have a class of functions. So what is the role of this capital H? The role of this capital H is that I gave you a guarantee that F comes from this capital H. You have the guarantee that F comes from capital H, but you don't have to output something from H. The algorithm ERMH will output something from H, but it's not a requirement. You just have to output some predictor function. Right? So if you go back to the examples of the papaya, I give you a guarantee that there exists some rectangle in the softness color space that classifies the tasty versus non-tasty papayas. But as your prediction rule, you're not obliged to use a rectangle. You can say, okay, we know that there is such a rectangle. It'll be easier for me to approximate it by something like that. Yes?
Doesn't that mean that theoretically there exists a learner which always helps a good function?
I don't hear you.
So, I mean, there always exists the right function, right? We're assuming that. So doesn't that mean we can theoretically create a learner that always helps the right function?
Okay, so that's a valid question. He is suggesting a cheat. He says that we assume that there is a function that predicts well. Why don't we output that function? The point is that the learner is only allowed to take as input the sample. And it has to be correct for every f and every distribution. So you don't know what f there is, and you don't know what is the distribution, and all you see is the sample. It's kind of like we are playing a game. You are the algorithm, okay? Now I pick a function trying to mislead you. And I pick a distribution that's trying to mislead you. And you're telling me, no matter how hard you try, you picked f and you picked the distribution, no matter how hard you try, once you show me enough samples, I will be correct. So if you fix your predictor as f in advance, I'll just pick another f. Because I can pick any function from the class H. Okay? This is for every function in f, in H you should succeed. Yes?
Accuracy and confidence are independent of each other? Like
Accuracy and confidence are independent of each other. Just think of that, right. Accuracy is, say I'm trying to predict the temperatures tomorrow. Oh, so I'm telling you the temperatures tomorrow will be maximum -10. And if it will be -11 or -9, that's my accuracy, and you will not consider it a big error. But there is also a small chance that there was some storm coming and I completely didn't see it, and the temperature will be -30 tomorrow. So that's the delta. The small chance that things will go completely off. And the epsilon is what is the accuracy that you will tolerate. You will tolerate ±1 degree. Yes?
So you say that A has to satisfy every every F is...
The algorithm has to be able to handle every f. Right.
When it's handling something, it's only handling that particular F. It's taking the sample from that particular
Right.
F.
It takes a sample from that particular f. That's its clue how to handle that f. But all that my algorithm sees from f is the sample. Okay? So learning is, again, this idea of getting from experience to expertise. My experience is what I see in S, and I'm becoming an expert if I can give you a rule that will hold. I kind of detected what was the F. So we already saw something. So if I rephrase what we saw last week, which I just repeated at the beginning of the class, we already saw. So if we can rephrasing last week's result, we get that theorem, every finite H is PAC learnable with the function mh epsilon delta being the bound that we just saw. Mh epsilon delta being at most, what should be the mh? I'll write it here. I'll calculate it in a second. It's going to be log the size of h plus log ln the size of h plus ln 1 over delta divided by epsilon. Furthermore, any ERM H learner will be successful. So what I'm saying is that what we showed at the beginning of the class today, or last time, is actually that every finite class is PAC learnable. How do I get this bound? What did we show last time? Last time we showed that the probability of success, we showed last time that the probability over S coming from D to the M labeled by F, that the arrow LDF of A of S will be greater than epsilon is at most the size of H times e to the minus epsilon m. That's what we showed. Right? Now, if I want this to be, this is the probability of failure. Which parameter in my definition of PAC captures the probability of failure? Which parameter is it that talks about the probability that I will fail to approximate? Delta. So I want this to be less than delta. I want this to be less than delta, because this is my probability of failure. So I just look at this equation and take a log of this equation. So I get ln of this equation. So I get ln h plus minus epsilon m should be less than ln delta. Yes? MH is the smallest number that suffices for learning. The smallest number that suffices for learning is at most this, because this suffices. So MH is your guarantee. If I have MH samples, then I will succeed. I'm saying there is some MH, it's at most this. This definitely will suffice. And once you have MH, you say every bigger M should do well. MH is like the minimum number of points that you need. If we show that this number suffices, then the minimum number is at most this. Yes?
What's the second ln term in that equation? It's ln side of h and ln
Delta.
on the left-hand board.
Here?
Go a little bit more.
Here.
Yes.
1 over delta.
1 on the
We'll get there in a second. I'm just rearranging this. So if I want to find m, I'm saying epsilon m is greater than ln h minus ln delta. But minus ln delta is ln 1 over delta. So I get that m should be greater than ln h plus ln 1 over delta divided by epsilon. And that's the result that I have here. So I just rearranged. Yes?
It's not clear to me that we actually need the probability in the definition of PAC. Because look at that expression, it's like,
This one.
yeah, it's the probability of a probability less than delta.
It's the probability over samples.
Yeah, so,
When I take, this is an expectation. It's not a probability.
so if you modify the definition to just say that L is greater than epsilon,
But I cannot just say that L is greater than epsilon, because L depends on the samples. Some samples may be very bad, and the algorithm may fail on those samples. So there is inherent probability here over the samples. I pick the samples in an IID way. right? Now assume that I'm just unlucky, and I pick time after time after time the same sample point. Then I cannot learn. But the probability that I'll pick time after time the same sample point is very small, so it's covered by this delta. So this is just the probability that I'll pick a bad sample. If the sample is good, I will do well. Yes?
So the end goal is you want to find the sample size so that delta and epsilon, if you know delta and epsilon, you can find the sample size
Exactly.
to give you a minimum.
Right. I should find a sample. You give me epsilon and delta. That's your specification. That's what you want.
Right.
And as a function of this, I can tell you how many sample points I will need. And this is without knowing anything about the distribution and without knowing anything about the labeling, except that the labeling came from H.
And H will be a set of those sample points.
H is a set of functions.
Set of functions.
It's a set of functions from which F was picked. If we go to the papayas, H is a set of all rectangles. Yes?
What if all of the H is actually a bad set, so all functions in H are bad?
Okay, it cannot be here, in this definition, it cannot be that all of H is bad, because we guarantee that the correct labeling come from H. But that's a very strong assumption. I will discuss it in a minute. I mean, this is, okay, so I will, just wait a second, I will discuss it, because this is the next point I want to discuss. And then you can come back with the question if I didn't answer it, okay? Yes?
It's strong because you assume that there's some perfect function. in
Right.
H.
It's strong because I assume that some perfect, okay. So let us just take a step, yeah.
I might be jumping ahead, but is there a way to kind of ensure that your H is good? How do you do that?
That's exactly what I'm going to talk about now. Okay. Yes? What? Yeah, it's a question that someone already asked. MH, it's a bit confusing. MH of epsilon delta is the minimum number of points that will suffice. The minimum number that will suffice is at most this. Anything bigger than this MH should be okay. Any sample size bigger than MH should be okay. All right, so we have our definition of, I'm with you in a second. We have our definition of PAC learnability, and we showed that finite classes are PAC learnable. And the next thing I want to discuss is what are the merits and the weaknesses of this definition, and then we will improve the definition. Okay, so the strengths of the PAC definition is that we can guarantee the number of needed examples for training regardless of the data distribution D, and of which F in H is used for labeling. Right? Because our sample size M depends only on the accuracy and confidence parameters. So that's the strength. I mean, compared to classical statistics, I don't have to assume that my distribution is normal. I don't have to assume that the behavior of the data is linear. I don't have to assume anything. It is completely, we call this merit, we call it, this is a distribution-free guarantee. That's the strength of it. I give you some number m, you can be sure that it will be okay. What is the weakness of the PAC definition? So the main weakness I think that you should note, or weaknesses, main weakness is that we assume it only works if the labeling rule F comes from H. And that's very unrealistic. That's very unrealistic that I will know if I want to predict if a papaya is tasty or not. I have to assume here that there is a rectangle of taste, of color and softness, such that every papaya inside this rectangle is tasty, and every papaya outside this rectangle is not tasty. And that's not a realistic assumption. So in fact, the first relaxation that we are going to make is we are going to relax this condition. This makes it unrealistic. We are going to relax it. And we are going to relax it in a very strong sense. Not only that I will not assume that F comes, that the labeling rule comes from H, I even don't assume that there is a labeling rule. Maybe you cannot detect the taste of a papaya from just looking at its color and softness. Maybe there could be two papayas that look the same, feel the same, but one of them is tasty and one of them is not. We also want to be able to model such situations. So we relax not only the assumption that F comes from H, but even the assumption that there is such an F. So here is our relaxation. We want to be able a situation in which instead of a probability just over X and the labeling rule, the data is generated by some probability distribution D over X cross Y. So not only the papayas are picked randomly, but also the taste is being picked randomly. You have a distribution, and there is some probability that you will see a papaya with a good taste, and there's a probability you will see a papaya with a bad taste. And distribution is not only over the color and softness, but also a distribution over the taste. The taste is also random. So we want to strengthen the definition now and want to say, can we learn in a scenario in which the labels is not even determined by a function, let alone that I don't know that this function comes from my class? Can we do anything in such a situation? Yes?
You output a distribution instead of a function.
What?
Or instead of outputting a function, you output this distribution.
I want to predict. I want a prediction rule. So, I mean, you want to predict whether to buy this papaya or not. So I want to give you, you have your papaya in hand. I want to tell you, buy it, don't buy it. I don't want to tell you, I mean, I could tell you, flip a coin and decide according to the coin.
So the distribution as a function of the papaya parameters.
So I want as a function of the papaya, what I want to output, we still want to output, we still wish to output a labeling rule. What's a labeling rule? It's a function or hypothesis that goes from x to y. You take a papaya, and I tell you what is going to be the taste. I want to give you a prediction. So think of weather. I have all kinds of measurements. The x is all the measurements that I make today, and the y is the weather tomorrow. So the y could be the temperature, the precipitation, whatever, right? But it's very clear that there is not a single deterministic function that if I give you all the data of today, you will be sure what is the weather tomorrow. There's kind of randomness there. And I want to give you a rule, that will give you some prediction for tomorrow. So, first of all, what is the best rule that I could give you? So assume, that's our goal. So assume again that y is just binary. What will be the best rule? What will be, I'm claiming that the best predictor f or h should be, anybody has an idea? The predictor only sees x, and it needs to predict a label, and everything is random. What will be the best thing I could do? Yes?
Just guess.
Just guess, but I want to give you an instruction of how to guess smartly, right? Yes? We are getting there. What I can do, the best rule will be that h of x will be as follows. Let's call it h star of x. This is the best predictor. It will be 1 if the probability of x with label 1 given x is greater or equal than a half. And it will be 0 otherwise. So what will be my rule? You see x. Then you ask, given that this is the x that I saw, what is the probability that the label will be 1? If the probability the label will be 1 is greater than half, predict 1. If it's less than a half, predict 0. This is called the Bayes rule.
Shouldn't that be y? Probability of that y is 1, that x is 1, it should be y.
You see, the probability gives you x and y. So I'm asking, given x, what's the probability that you will see x with label y equals 1?
Okay. Well, that's a y. It's like an x.
This is x.
This is x. That's also x.
This is also x. You are given x, and you ask what is the probability of x with label 1. Given that you know what x is, what is the probability that you will see it with label 1? Given that you see the papaya, what is the probability that this papaya will be tasty? So that you will see such a papaya with a tasty label. Okay? So if given such an x, the probability that you will see 1 is greater than a half, the best will be to predict 1. And if given that x, the probability that you will see 1 is less than a half, predict 0. Yes?
But still, are we making the assumption that there is some relationship between x and y?
Okay, what is the sum? I'm not making here any assumption, except that I have some, what we call the data generating rule. How is the data generated? There is a distribution that picks randomly a pair, x and y. So the distribution picks a pair, x and y. And the best rule will be to look at the conditional distribution. Given x, is it more likely to come up with an x1, or is it more likely to come up with an x0, given this x? Now, I think you have a good intuition of something is fishy here, and I will explain the fishiness in a second. Yes?
So practically, like this distribution should be made to resemble our sample.
What?
Like, I mean, I understand, like, this distribution could be anything random, right?
The distribution could be anything random. So I think maybe you are alluding to the same issue that bothers him. Because if I could just output the base rule, then I don't need any learning theory. I don't need any learning at all. Here is the best rule. Given, if you want to predict the weather, here is the best rule for you. Given the conditions today, if the probability of snow tomorrow is greater than a half, predict snow. If the probability of snow tomorrow is less than a half, predict no snow. What's wrong with this rule? Why don't people use it?
You don't know what's going to happen tomorrow.
Because we don't know the probability. I mean, this would be a good rule if someone came to us and told us this is the probability. But this rule depends on knowing the probability of seeing this pair when I know that this is x. I don't know this probability. The problem is we do not know D. We only see a sample generated by D. So the whole problem of learning is that the universe is, you can think of it as some distribution over events, but you don't know what this distribution is. So you're trying to predict based on just a sample. If you knew the distribution, the prediction rule would be very simple. For a coin, for example, if I have a coin which is not biased, I know what is distribution. Distribution is half the time it will give you 1, half the time it will give me 0. It doesn't matter what I predict, I'll make half an error. If you have a biased coin, if you want to cheat in some game and you have a dice which is biased in the casino, so you predict the label which is most likely to come up with your biased dice. But the problem is that you don't know this distribution. What can we do? And this is what learning is coming to help us. How can we, based on a sample, get close to knowing the distribution? Okay? So my next step, okay, let us just, what have we done so far? We said the assumption that the labeling rule comes from H was too strong. We want to relax it. So we'll relax it a lot. We talk of a data generating mechanism such that the distribution over X and labels. And under this situation, the best that we can hope for is this base rule. If what we are trying to predict is the outcome of a coin, the base rule will tell me predict 1 all the time, it doesn't matter. And what will be the probability of failure of this rule if I just try to predict the tossing of a coin? Half. It'll be very bad. So under this situation, we redefine the notion of successful learning. So we now redefine successful learning to have only a relative error guarantee. What do I mean by a relative error guarantee? I cannot guarantee that you will be able to predict the coin flip. But I can guarantee that relative to the best possible, you will be doing pretty well. So if you are trying to predict something which is completely random, I will be happy if you give me a completely random conjecture. But I want that if you're trying to predict something that is predictable, you will do better than random. So the guarantee now is going to be relative, and we'll see in a minute relative to what. Rather than guarantee that you will not make error greater than epsilon, we make a relative guarantee. So here is the new definition. So this is my revised definition of learnability, and it's called the definition of agnostic PAC learnability. And agnostic comes to say we don't make any assumptions. We don't believe in anything. The nature can be as unexpected and unpredictable as possible. We still want a notion of what does it mean to succeed in learning. Okay, so what is agnostic PAC learning? We say that a class H, a class of predictors H is agnostic PAC learnable if now it will look very similar to the previous definition except for the last formula. So if there exists some function m h of epsilon delta, as before, that goes from 0, 1 times 0, 1 to the natural numbers. And a learner A. A learner, as before, taking samples, outputting predictors, as before, such that for every d over x cross y, so now I don't require this f belongs to h. I don't require any f at all. I have any distribution over x cross y. Every epsilon delta greater than 0, the probability of a samples generated by d to the m that a, the arrow LD of A of S will be greater than, but now I cannot guarantee that you are not going to be greater than epsilon. What I'm going to guarantee is this is greater than the minimum over all h in H of the arrow of this H plus epsilon will be less than delta whenever m is above this mh of epsilon delta. Okay, so let us just look at this new definition. It is very similar to the old definition. But what have we changed? The only thing that we changed is that instead of giving you a guarantee that I will never make an error greater than epsilon, my guarantee now is that I will never be epsilon worse than the best h in H. So this is a relative guarantee. If my distribution is so bad that nobody can predict, then the minimum error of every predictor in H could be a half. And therefore, I'm saying, OK, my error will not be more than a half plus epsilon. I mean, I say nothing. So this is only a relative guarantee. Rather than telling you I will not make error greater than epsilon, I'm telling you I will not make an error greater than epsilon more than necessary. And what is necessary? Necessary is the best behavior of someone in H. So the role of H changed. Before, H was my collection from which the data was labeled. Now, H is just the class that I compare myself to. So if I want to give you, for example, I want to give you a guarantee for weather forecasting. So I'm telling you I can predict the weather very well. There is very small chance that I will err more often than the best news channel. I'm just comparing myself. So this capital H is the set of all predictors of the news channels. And I'm giving you a guarantee that I will never be worse than the best of them. But for every distribution, someone else from them will be the best. So it's not so vacuous. Think of it, I can take H, say H is all the computer programs that run that can run and get an output within 2 minutes. So I give you a guarantee that my prediction will be as good as the best program that can run in 2 minutes, plus maybe a slack of epsilon. And this is no matter what the underlying distribution is. So maybe the underlying distribution is terrible and every computer program will fail. I'm allowed to fail too. But if the data is very simple and some computer program that run in 2 minutes will succeed, I guarantee that I will succeed as well. Right? Or I can give you a guarantee for the stock market, invest with me, and your profit will be very close to that of the best from this big investment group. So you can check me in retrospect. Maybe there was some world catastrophe and all the stock markets collapsed. I cannot do anything about it. The only thing I can guarantee is that if I fail, everybody else fails. If someone succeeds in this group, I will also succeed. So H now becomes the group that I have to compete with. Who do I guarantee that I will be able to compete with? Okay? So that's our new definition. It is a much more realistic definition. What we will do next time is we will show that under this realistic definition, again as well, we can again show that every finite class is learnable. Thank you.